Okay, this is Math 156, Lesson 9. If you compare this course to the Math 176 syllabus, you see that almost the first half of the course means up to Lesson 14, is integration. And we already saw that to integrate in Maple, you just need to use the initials INT. So all the skills you learn, substitution, integration by parts, and so forth, are extremely important as calculus mathematics technique. But in Maple, you just say integrate, and Maple integrates. One technique that it's interesting to know you can sort of see done before your eyes in Maple is to expand a rational function in partial fractions. So, for example, if we take this example, this rational function, we want to convert it to partial fractions, and the simple command is, it's simple, but you have to get the syntax right. Convert the expression you want to convert. Par frac means partial fractions. X. Expand this as a partial fractions in X, and you do it, and lo and behold, that's what you get. Now, if you take the original function and you integrate it, you see this is what you get. And instead, of course, if you put in the partial fraction expansion, you get this. Of course, what this really is, let me do it slightly differently. Let me write it. Let me see if this works. I'm not sure. Let me just copy this whole expression. Copy, insert. So let's say that I just want to do the first partial fraction, which is X, subtract the second partial fraction, which is 1 over X squared, and add the third. So this is the integral of X minus the integral of 1 over X squared plus the integral of 1 over X minus 1. That's integrating this term by term. And if we put this together, we get exactly the answer, of course. So you could, what I'm doing is doing these three integrals separately. Maybe if it's clearer if I do it like this. So this is the integral of X. This is the integral of 1 over x squared. Oops, this should be a capital I. There we are. So here we have this function, a rational function, that means a quotient of polynomials, converted to partial fractions. So let me just rearrange this so it looks a little bit more interesting. So in Maple, here's the function. You want to integrate it, you just integrate it. But if you want to see how you would do this by hand, you would convert it to partial fractions. And integrate the partial fractions. But really, to see what's going on, let me get rid of this. If we integrated the first term, we would get x squared over 2. If we integrate the second term, we get minus 1 over x. If we integrate the third term, we get log of x minus 1. And these are the 3 terms. So you just see how Maple has done all this, but it's... So that's all it is. I mean, there are a lot of homework problems where you have to convert things to partial fractions. Let me just do one so you see how easy it is to do these things in Maple. In lesson 13, number 27 was to integrate x squared plus x squared plus 5 divided by x cubed minus x squared plus x plus 3. X squared plus 5 over x cubed minus x squared plus x plus 3. And the homework problem in Math 176 is to integrate this by partial fractions. Let me just give this a name. I'll just call it G. And so let's say we want to convert G to partial fractions. You can actually leave out the x because there's not a second variable that you have to worry about. So that's the partial fraction expansion. If we integrate this first expression, we get log x plus 1, of course. If we integrate the second expression, we get this arctangent. So the integral of G is the integral of the first term plus the integral of the second, this plus this. And if we just have Maple do it directly, we get exactly the same thing. Log x plus 1 plus this arctangent term. So that's all it is. There's a simple command to convert a rational function to partial fractions, if it's possible. It does depend on the being able to factor your expression into polynomials with integer or possibly rational numbers as the coordinates, as the coefficients. lesson 15. In Math 176 has to do with what are called improper integrals. So there are various kinds of improper integrals. You might have something like the integral of 1 over x cubed as x goes from 1 to infinity. Oops. That should be an n. Yeah. Now, the way you learn how to do this in Math 176 is this is a limit of the integral from 1 to b as b goes to infinity. Yeah. So this is exactly how you define an improper integral in Math 176. This integral of the first kind, where you have a finite lower limit and you're going to infinity is the upper limit. So the way you would do this by hand is well, so you can't calculate this because it needs to know what b is. So you would take a number like maybe 100. And or a number like 1,000. Let's write this as a decimal. Or a number like 10,000. We're going further and further out. Or even a number like 100,000. Yeah. I mean, this is only, you have 10 decimal digits here, so this is not exactly a half, but, and then you would take the limit. But of course, in Maple can just automatically calculate these improper integrals. And it tells you the improper integral is a half. So the definition of the improper integral is the limit, is this limit. But, and then you calculate by computing the limit, but Maple does it all for you. I mean, that's why we have Maple, it's pretty good. There's another kind of improper integral, which happens when your function is going to infinity. Like when x is 0, this function isn't defined. Let's say from 0 to 1. And happens if we try to compute this in Maple? So according to Maple, this function diverges. This improper integral is infinite. How do you define the improper integral in your calculus class? So the integral from 0 to 1, so this function is discontinuous at x equals 0. You would take the limit of the integral from a to 1 as a goes to 0. This is how you define this kind of improper integral. The function is discontinuous at x equals 0. You go a little bit to the right, you take some positive a, you compute the limit from a to 1, and then you take the limit as a goes to 0. Actually, I should have, the way we write limit by hand is LIM, but in Maple, we write LIMIT. So this is the right way to do this. So when I went to explain how we express this as a limit, it's like this. It's the limit of the integral from a to 1 of 1 over x cubed as a goes to 0. That's the improper integral. And let me just do a homework problem from lesson 15. In lesson 15, so here's an interesting problem. Here's I take the integral of the function 1 over e to the x plus e to the minus x. This is number 33. What does the graph of this function look like? Suppose I plot say x going from 0 to 10. It's decaying pretty fast. So what does this integral look like? The integral is the arctangent of e to the x. So that says if you differentiate the arctangent of e to the x, this is what you get. Let's check that. So arctangent e to the x, as I've written it, is an expression, not a function. So I use the diff command. So differentiate this expression with respect to x. And that's what we get. Is it the same as this? Let's see. Let's see what happens if I say simplify. Oh. Let's try this. Well, you can see it's the same thing because this denominator is the same as e to the x times e to the x plus e to the minus x. The e to the x is canceled and you get this. Oh, sorry. This is the indefinite integral. I want to integrate this from 0 to infinity. It's pi over 4. Wow. Why is that? Because we saw that the indefinite integral was arctangent of e to the x. When x is 0, arctangent of 1 is pi over 4. As you go to infinity, arctangent of e to the x goes to pi over 2. If you plot arctangent of e to the x, it looks like that. This is approaching pi over 2. So can Maple calculate arctangent of infinity? Pi over 2 minus arctangent of 0 let's see. Let me just insert a line. Oh, arctangent of e to the x, that's right. So arctangent of e to the infinity minus arctangent of 1. That's pi over 4. So when Maple calculates the improper integral in one step, you get the answer of pi over 4. If you want to understand a little bit more about what's happening, the indefinite integral of this function is the arctangent of e to the x. Function decays like this. So the arctangent of e to the x as x goes to infinity is the arctangent of infinity. That's pi over 2 minus the arctangent of the x of e to the 0, arctangent of 1, which is pi over 4. Pi over 4 from pi over 2 is 1. Let me just actually write these things out exactly. So it's just interesting to see. Oops. That's not what I wanted. So let me copy that. All right. So the arctangent at infinity is pi over 2. The arctangent at e to the 0 of 1 is pi over 4. When you subtract, you get pi over 4. That's what we wanted to say. Let's do one more example from the text. This is number 49. We have the integral of the function 1 over the cube root of x minus 1. That's x minus 1 to the power 1/3. As x goes from 0 to 2. Now, this is an improper integral because when x is equal to 1, the denominator is 0. Let's just see in one step whether Maple can solve this problem. Oh, that's weird. So this says we get some imaginary number, some complex number. Suppose we look at this function. And we plot it from 0 to 2. So for some reason, Maple only wants to graph this from 1 to 2. Does that make it easier? So as x goes to 1, this is positive, but going to 0. So this is going to plus infinity. Huh. Now, when x is less than 1, this is negative. Cube root is negative. I don't see why the function doesn't want to graph this. Complex values with the time perspective. So it has no problem graphing the cube root of 1 minus x from 0 to 1. But it does have a problem oh, so it just did it. I don't know why it had a problem before. So this is the graph from 0 to 1. This is the graph from 1 to 2. Let's see what happens if I try to put them together. I don't know why it doesn't want to do that. But you can see the graph of this function, it has a singularity. It's not continuous at x equal 1. It goes up to infinity, and in this direction up to infinity. So let's see what happens when we try to integrate this. Why does it want to give us a complex number? We're doing the experiment. If you integrate from 0 to 1, it wants to make this, 0 to 1, 0 to 1. Suppose I make this to 0.9. Still wants to make it complex. I don't understand why Maple is acting this way. You might want to experiment with this. Let's make it look at a simpler integral. Let's look at the following integral. The integral of x to the 1/3. And suppose we want to integrate that. Of course, we know what that is. That's the indefinite integral. Now, as x, if you integrate this from 0 to 1, you get 3/2. Let's see what would happen if we integrated this. I think the problem is that Maple just doesn't like these improper integrals for negative numbers. Oh, no, it has no problem with that. But this is complex, right? Square root of -3. So Maple just doesn't like these negative numbers. So if we go back to this original problem, this one, suppose we wanted to compute this integral from 1 to 2. So from 1 to 2, this is positive. And it gives us a value 3/2. It's just what we would expect. But it doesn't want to do this for a negative number there. So let's just leave it with that. No, nothing is perfect, and not even Maple. Oh, okay. So in the next homework assignment, I'll give you a few problems to do using Maple to compute partial fractions and to compute some improper integrals. And you have to realize that improper integrals do not necessarily exist. Sometimes they do, sometimes they don't. So for example, we see that this improper integral exists, the integral from 0 to 1 of x to the 1/3. But if we change that to the integral of let's take this out. The integral of 1 over x cubed. That's infinite. That improper integral doesn't exist. Yeah. So this is our lesson for today. Improper integrals and partial fractions. In the next lesson, we'll look at infinite series and Taylor series, Taylor polynomials, and then we'll do some differential equations. That's basically the rest of the syllabus. Okay, that is it for now.